Welcome to the video for Chapter 4 Notes, Part 1 for Lesson 4.1. Chapter 4, we are going to be learning about probability and counting rules. And specifically in 4.1, it's all about sample spaces and probability. So in this lesson, we're going to learn some basic concepts about probability. We're going to learn about the three types of probability. We're going to learn about complementary events, the large law of numbers, and a little bit about probability and risk taking. So some basic concepts. A probability experiment is a planned operation carried out under controlled conditions. A result of an experiment is called an outcome. The sample space of an experiment is the set of all possible outcomes. So in our class, we're going to be learning about some different ways of looking at probability, and a few of them are going to be flipping a coin, drawing a card from a deck of 52 cards, and rolling a six-sided die. So I'm just going to talk through some ways we use these. If we were to roll two six-sided dice, we could have a total of 36 possible outcomes. One of those outcomes could be where die 1 rolls a 1 and die 2 also rolls a 1. We could also have it all the way where die 1 rolls a 1 and die 2 rolls a 6. So there's 6 ways that die 1 will roll a 1 and die 2 would roll the 1, 2, 3, 4, 5, or 6. All the way down to when die 1 rolls a 6 and die 2 rolls a 6. And you can see on the diagonal, these are outcomes where they're matching 1, 1, 2, 2, 3, 2, 4, 4, 5, 5, and 6, 6. Also something that we use if you're playing crap at the casino, they go by rolling two six-sided dice such as this, but they go by the sum of the die. So there's only one of the 36 outcomes in the sample space where the sum is 2. There are 2 where the sum is 3. And then you can see on this diagonal, it keeps going. There's 3 where the sum is 4. There's 4 where the sum is 5. There's 5 where the sum is 6. And when the sum is 7, that is the most that you'll have. And that's 1, 2, 3, 4, 5, 6. So 6 out of the 36 have a sum of 7. And then it goes back down again to 5 possibilities, 4 possibilities, 3 possibilities, 2 possibilities, and 1. Playing with a deck of cards, a lot of us grow up playing card games, but there are many of us that do not. So I want to go over how a deck of cards is set up. The different shapes on the deck of cards are called the suits, and there are hearts, diamonds, spades, and clubs. These right here are called the spades, and this last one are called the clubs. They look kind of like a clover, but there's 3 leaves instead of 4 leaves. So there's 4 suits, and there are 13 cards in each suit. So 4 times 13 is 52. And a lot of times this is the ace, and the ace is a lot of times treated as a 1. Sometimes it's treated as the highest card. It just depends on the game you're playing. And then we have the jack, the queen, and the king. Those are called face cards because they have faces on them. Okay. An event is any combination of outcomes. So remember on the prior page, page 74, we talked about what an outcome is. An event is a combination of outcomes. An event with only one outcome is called a simple event. An event with more than one outcome to satisfy the conditions is called a compound event. Let's look at example 3 to explore that. Classify each statement as an example of either a simple event or a compound event. So if we roll a 6-sided die and we get a 4, the question that we want to ask ourselves, is there more than one way to get a 4? And there's not. It's just one single die. And so this is a simple event. You can only get that in one way. But if we were to roll a 6-sided die and get an odd number, there's more ways to satisfy the odd number. We could get a 1, a 3, or a 5. So this would be considered a compound event. And so the outcomes in this first sample space would just be 4. The outcomes here would be 1, 3, and 5. And then number 3 says having 2 children and both having the same color of eyes. There are more than one ways that you could do that. They could both have brown eyes, they could both have blue eyes, they could both have green eyes. So this would also be considered a compound event. Sometimes when we're looking at different probabilities and different types of events, the possible outcomes get a little complicated to keep them straight. And so a tree diagram is a special type of graph that we use to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. So let's say you wanted to see the sample space of all the possible outcomes for the gender of a family having 3 children. And I'm going to show you that below here. So this first limb here is the first child. It could be a boy or a girl, labeled with B and G. The second child could also be a boy or a girl, but it depends on if you had a boy or a girl first. So you could have a BB, a BG, a GB, and a GG. And then we add on the third child here. That could also be a boy and a girl. So our actual final outcomes in the sample space are listed here. Simply making the tree does not assume that the reader knows your sample space. You actually have to list out your sample space. So you could have all the way from all boys, boy, 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 with a bunch of combinations all the way down to girl, girl, girl. And if you're curious about how do we know how many are going to be in my final sample space, we're going to take the number of possible outcomes for each time we run the event. So there are 2 possible outcomes in the first child, and we're going to multiply those. It's called the multiplication principle. And there's 2 possibilities for the second child, and there's 2 possibilities for the third child. So that becomes 2 to the third, or 8 possible outcomes. And we can count those here. 1, 2, 3, 4, 5, 6, 7, and 8. I always like to know when I'm making these, how many possible outcomes am I going to have? And always try to be consistent. Notice I always labeled my boy on top of the girl each time, and you could have done it the other way, but it's just so you've got consistency so that you make sure that you're not getting them mixed up. So let's do example 2 together. It says, if you were to roll a 6-sided die 2 times, draw a tree diagram to display the sample space of outcomes after the 2 rolls of the die. So I'm going to start up here. That is a 1, 2, 3, 4, 5, and 6. And then under each one of these, oops, I smeared my 4. Under each one of these, we're also going to have 6 rolls because I could roll a 1 on the first die. So this is die 1. And then this is going to be die 2. So I'm going to have 1, 2, 3, 4, 5, and 6. And then I'm going to do the same after I roll and I get a 2 on the first die. I could also get a 1, 2, 3, 4, 5, or 6. And so essentially, we're just using, we're doing a tree diagram to show you what we did on the very first page of the notes, where I had it in a table form. This was definitely a little bit more organized for this type of an example. And then on the tree, you would do this all the way down to rows 4, 5, or the outcomes of 4, 5, and 6. Again, you would have 6 coming off of each of those. Let's talk a minute here about the 3 types of probability. So the classical probability is based on equally likely outcomes. So we've already looked at a few examples of those: rolling a fair die, drawing cards from a deck, and flipping a coin. All should have the equally likely outcomes of being drawn. Empirical probability is based on real life experiments, collecting data, such as collecting blood type on people. That's how they came up with likelihoods of different blood type. Now, you'll see that I think type A blood is the most common type of blood. So that's based on real life data they've collected over years and years and years. Whether somebody's traveling by plane or over Thanksgiving, that's again collecting empirical data. And then the third type of probability is the subjective data. It's based on opinion. And my famous example is the Lions are going to win the Super Bowl. I think this might be the year. Hopefully, when you're watching this video, they've already won the Super Bowl. So let's look at example 3. It says classify each statement as an example of classical probability, empirical probability, or subjective probability. Go ahead and pause the video, take your guess on these 4, and then we will come back together. Okay, we're back. So let's look here. The probability of getting 3 clubs when being dealt a 5-card hand. That is classical probability. Based on equally likely outcomes. The probability that a bus will be in an accident on a specific run is about 6%. That is based on empirical data they have collected. The probability that a person will watch the World Series is about 0.15. Again, that is based on data they have collected from past World Series. D says the probability of winning at a Chuck-a-Luck game is 5 out of 36. I've never played Chuck-a-Luck, but it is based on equally likely outcomes. Okay. So when I say equally likely, that means that each outcome of an experiment occurs with equal probability. Next up, we're going to talk about how to calculate probabilities. So calculating probability of an event when all outcomes in the sample space are equally likely, you're going to count the number of outcomes for event A and divide by the total number of outcomes in the sample space. So that will look like this: X over N. X is the number of outcomes that satisfy your question out of the total number of times you're going to run your event, number of times you're going to run your experiment N. It can be representative as a fraction, a decimal, or a percent. So for example, if you toss a fair dime, there are 2 outcomes, heads and tails. Capital H will be heads, capital T will be tails. And we note this as P of H. P of H is how you say that. That means the probability of H, meaning the probability of getting the heads, is 1 out of 2. There are 4 probability rules that we must follow. And the first one is each event is a number between 0 and 1. It could include 0. So there could be a 0 probability of an event occurring, and there could be 1 or 100% probability. So it's between 0 and 1 inclusive. The sum of all the probabilities of all outcomes is equal to 1. If an event E cannot occur, that means the event contains no members in the sample space. Its probability is 0. And if an event E is certain to occur, then the probability of E is 1. And I just put it on a number line here for you. If somebody says an event is impossible, we would think that that probability is 0. Unlikely is going to be somewhere between 0 and 0.5. If it's a 50-50 outcome, it's at 0.5. Likely is anything between more than 0.5, and then certain would be 1. The complement. And I'm not saying complement with an I here. That means that you're telling somebody their outfit looks nice for the day. We're talking about the complement. Sometimes it's noted called A prime here, or with a bar above it. I've given you a couple different notations. You might see them all. So A prime or the complement consists of all outcomes that are not in A. So that means the probability of A plus its complement has to equal 1. That also means that the probability of the complement is equal to 1 minus the probability of the event. And likewise, the probability of the event is equal to 1 minus the complement. So all three of these equations can be used. So let's look at example 4. Let's let S be a sample space of 1, 2, 3, 4, 5, and 6, and let A be the sample space of 1, 2, 3, and 4. Let A prime or the complement be equal to 5 and 6. What is the probability of A? So A is the probability of all of the outcomes that are in A. So that's 1, 2, 3, 4 out of S here. 1, 2, 3, 4, 5, 6. So that would be 4 out of 6. What is the probability of A prime? That would be all the outcomes in S that are not in A. So that's outcomes 5 and 6. There's 2 of those. So that would be 2 out of 6. There's no need to reduce here. And then what is the probability of A plus the probability of A prime? And so that would be 4 out of 6 plus 2 out of 6 would be 6 out of 6, and that should equal 1. Let's look at examples. If a card is drawn at random from a deck, find the probability of getting these results. Of getting the result of a 6 and a spade. So to get a 6 and a spade, there's only one card that satisfies that. So that would be 1 out of 52. To get a king, there are 4 kings in a deck. So that would be 4 out of 52. To get not a heart. To get not a heart would be, you could count all of the things that are not hearts, or you could use the complement. So that would be the probability of not a heart, looks like this, is equal to 1 minus the probability of a heart. So we can use the complement. So 1 minus the probability of getting a heart means there are 13 cards that are hearts. So that means 1 minus 13 over 52 is 52 minus 13 over 52 is 39 over 52. And what is the probability of a diamond or a heart? So that would be 13 out of 52 plus 13 out of 52. So that would leave 26 out of 52. Last type of graph or picture we're going to do for probabilities is called a Venn diagram. A Venn diagram is a picture that represents the outcomes of an experiment. It generally consists of a box that represents the same space, represents the sample space, and with circles or ovals. And the circles or ovals represent events. So we've got one here. We've got an event A that has outcomes of 1 through 6. We've got event B that has outcomes of 6, 7, 8, and 9. Then we have event A and B, and you can see that's 6 because that's where they overlap. A and B means that the outcome has to be in both. A or B means it could be in one or the other or both. So that looks like 1 through 9. The Venn diagram is as follows. So you can see outcomes 10, 11, and 12 are not in A or B. Let's look at example 6 to try drawing one ourselves. So it says, suppose an experiment has outcomes black, white, red, orange, yellow, green, blue, and purple, where each outcome has an equal chance of occurring. Let event C be green, blue, and purple. Let event P be red, yellow, and blue. C and P is blue. Blue happens in both. C or P is green, blue, purple, red, and yellow. Draw a Venn diagram representing this situation. Okay, so I'm going to draw a big rectangle. And then I'm going to draw 2 ovals, and I'm going to overlap them because I do know there is an overlap. We said blue overlaps, so we've got C and P, and blue is in both. That's what it tells us right there. So I'm going to circle that. So we use that information. And we know that in C, we've got green, blue, and purple. I've already written down purple, so we're just going to write green and blue are in C and only C. And then P has red, yellow, and blue. We've already written down blue, so that means P has red and yellow. And so we've written down yellow and green and blue and purple. And red. So black, white, and orange if not. So I'm just going to fill those in down here. So black, white, and orange are not in either C and P. Let's try one last Venn diagram. Example 7 on page 82 says 50% of the workers at a factory work a second job. 25% have a spouse who also works. 5% work a second job and have a spouse who also works. Okay. So draw a Venn diagram. W is going to be works a second job, and S has a spouse also works. So I'm going to draw a big rectangle. So we've got a W and an S. And do they overlap? It looks like there is an and here. So they do overlap 5%. Okay, so I'm going to draw 2 ovals and they do overlap. And it says 5% work a second job and have us. Okay, so this is 5%. Okay, so I'm going to just cross that off. We use then it says that 50% of the workers at a factory work a second job. So this W is a total of 50%. That means if 5% was the overlap, that means I have 45% that work a second job, but don't overlap with the spouse that also works. And then it says 25% have a spouse who also works. And again, 5% of that overlaps. So that means I have 20% who has a spouse that also works, but does not work a second job. And this is 45, 5, and 20. Which adds up to 70%. And so that means 100% minus 70% means that I have 30% of people that work a factory job, but they don't fit either of these scenarios. So that is just going to be the extra 30% out here. So sometimes there's little bits of information that you have to kind of put together. So the last little bit of this lesson, we're going to just talk about law of large numbers and risk taking. So law of large numbers is a theorem that describes the result of performing the same experimental experiment, a large number of times. According to the law, the average of the results obtained from a large number of trials should be close to the expected value and tends to become closer to the expected value as more trials are performed. So if you go to the casino and you happen to win on your first, you put money down on red 34 and it wins, it doesn't mean that it's going to keep coming up. The law of large numbers says that eventually you'll probably lose your money, or eventually all of the numbers will come up. But that's just the law of large numbers. So something to think about. Much of what we do in life has probability and risk taking. Some things have bigger risks than others. Driving to work, you have a risk if you're driving in your car, if you're riding your bike, if you're walking on a very fast road versus a side road. We take risks with our money. We invest money for our retirement, right? And some of those risks might be very risky and some might be low risky, investing in the stock market. Eating food produced in a factory, you're taking a risk that hopefully those people at the factory made the food correctly. So there's definitely risks in everything that we do, and we have to assess those risks for ourselves and try to minimize them the best that we can with the information that we have. And this is just a little intro to chapter 4 in probability. Catch me back for the lesson 4.2.